Just until now, the anatomists have forgotten a tissue, have forgotten the fascial tissue.
There's a whole system out there that we haven't explored as a system.
Neurology, body perception, force transmission, elasticity, wound healing. There is scarcely a field in which fascia does not play a major role, and seen from today's perspective, an often surprising role.
It's a new buzzword, fascia. But what exactly is it? Found throughout the body, directly under the skin and deeper, it's a hidden whitish-coloured fibrous band of connective tissue. It accounts for roughly 20% of our body weight. Like cling film, fasciae envelop our muscles, tendons and organs and provide a link to our bones. For centuries, the physiological importance of the fascia was overlooked or underestimated. But now it's considered to be key to our health. Is it the answer to relieving one of the most common of all medical problems, back pain? Our search for answers takes us across the globe. In Maine, in the northeast of the United States, Thomas Myers trains physiotherapists. He's written a pioneering book on fascia, Anatomy Trains. Myers has long believed that the fascia is interconnected throughout the human body.
If somebody comes to me with plantar fasciitis, I very seldom get the best results from treating their plantar fascia. I get the best long-term, I'm talking about long-term versus short-term results from working on the lower leg, or up on the hamstrings, or even under the back of the head on the neck, because they're all part of a single system.
Myers is convinced that the body's fascial tissue is interconnected in countless lines, extending from the head to the foot, from one hand right across the shoulders to the other hand, even spiraling through the entire torso. He believes that when we have pain in one place, the cause can often be found in a totally different area.
If we were considering somebody with low back pain, there's lots of different causes of low back pain, and it can be sourced in the arches, it can be sourced in the knees, it can be sourced in the hips, it can be sourced from coming down from the shoulders. You can see the large triangle between the shoulders and the low back. Obviously, that's going to affect it. We're also looking for the relationship of how the low back handles the weight as the body goes forward. Just keep rolling forward in a tight loop, Laura, because we want to see whether the spinous processes are going away from each other. If they're fascially locked in some area, probably hard to see on the camera, but she's locked between L2 and L3 here. If I'm trying to resolve a low back situation, I can't afford not to look everywhere, because I don't know where the source of that is going to be, because the tensegrity of the fascial system will make it maybe show up in the low back, which is a very weak point for all of us. But that doesn't mean that it's sourced in the low back. I have to look at the whole pattern. I have to address the whole pattern if I have any hope of taking the pain away in any kind of permanent way.
Anatomy Trains is a Bible for therapists worldwide. But what is the science behind Myers' anatomy of connection?
Here, and then where does it go?
In Frankfurt, the German sports medicine specialist Jan Wilke is trying to find out. He's conducting research into whether such anatomical chains really exist. In a series of experiments, Wilke has looked for evidence of the backline that Meyer describes. Here, moving the ankle should trigger movement of the fascia at the back of the upper thigh. And in fact, the ultrasound indicates a gliding of the fascia there.
Zumindest unsere ersten At least in the initial findings of our pilot-type results, it appears that when I move something down there, if I stretch the lower thigh muscles, then it seems I can detect a strain transfer to the area of muscles at the back of the upper thigh.
The second experiment is more revealing, proving the fascial connection between the cervical spine and the leg, separated by the entire length of the back. First, Wilke tests the cervical spine's mobility. Then the subject stretches his leg. Wilke wants to know what effects the stretching has on the cervical spine.
So let's look at the results. We see here the mean value of the 5 repetitions that we just undertook. 108 degrees is the total mobility value averaged through the 5 repetitions, 4 degrees more than the previous test. So mobility is improved following the stretching of the leg muscles. We've seen an improved ability to bend and stretch the head in the area of the cervical spine. And that again seems to indicate a mechanical force transmission across the muscle fascia connections. In this case, from the legs to up here to the cervical spine.
Even if researchers haven't pinpointed all muscle fascia lines, working with a fascia roll on the upper thigh certainly affects more distant body parts, such as the neck. Wilke suspects that force is transmitted not only vertically, but horizontally as well.
How is this relevant to practice? Because ultimately, the goal of research is to make it application-oriented, to see if it provides an alternative for physicians or physical therapists or patients at home. So do patients really need to work on the cervical spine to relieve neck tension? Or can they, if they don't want to do that, maybe also work on the torso or the legs and achieve relief through a force transmission effect?
Jean-Claude Gambertou was the first to render the fascinating full-body network of fascia visible to the naked eye. In his long professional life, the hand surgeon from Bordeaux in France has performed countless operations.
In surgery, you see every day how the layers of connective tissue slide to and fro. But how does this connective tissue function? It's a question that so far no one has answered. I wanted to know how it functions so that I could reconstruct tendons better, because tendons too are connective tissue.
At the Institute of Hand and Foot Surgery in Bordeaux, Gambertou makes the world of the fascia visible with a special camera. He films the tissue inside the living body. His pictures have changed the way medical specialists view the fascia.
You see, those are the organizing fibers. It seems totally chaotic, but it isn't. It's what makes life possible in the first place. A perfectly efficient system. The more we research it, the more we understand the fascia and its structure. And this will open the door to new therapies.
The Italian city of Padua boasts one of the oldest universities in Europe. It was here that Galileo Galilei proclaimed that the sun and planets do not revolve around the Earth. And it was here in 1678 that the first woman in the world received her PhD degree. Today, the university's revolutionary tradition lives on in anatomy professor Carla Stecco. She's following in the footsteps of her predecessors, who here in the old anatomy theatre defied a church ban on human dissection. She's also continued the work of her father, conducting pioneering research into the fascia's purpose and function.
My father was among the first to be interested in fascia and how to manage fascia. At home, he was always talking about fascia. To begin with, I wasn't really convinced about the role that fascia plays. So I started getting interested in anatomy and wanted to uncover it in my dissections to understand how this tissue works.
Per visualizzare e capire effettivamente com'è questo tessuto.
Before starting today's dissection in the anatomy theatre at her faculty, Carla Stecco is explaining to her students what fascial tissue is, with the help of a grapefruit.
This grapefruit helps us to understand what the fascia is and how it's connected to the muscles. If I cut through the grapefruit, we see not only the flesh of the fruit, but also the fibrous components that divide the grapefruit into individual sections and support the tissue of the fruit.
In the course of the dissection of a human corpse, Stecco shows her students how the fascia is found throughout the body.
This is the fascia, the loose connective tissue which allows me to slide from one level to the next. Can you see how extremely fluid its structure is? How it can be moved with ease? Look how I can get into it. It's all made up of water, proteoglycans and tissue, and it's so beautiful.
Carla Stecco's research on fascia has helped reveal what we know today. Fascia exists everywhere in the body, in many shapes and consistencies. Directly beneath the skin is the surface fascia. The deep fascia envelops our muscles, and also our muscle fibers, like the skin around a sausage. The fascia also envelops our organs in a whitish skin. Even the brain is protected by this tissue.
We can even view the meninges as a special fascia, because ultimately it shares the same characteristics as fascia that we know from other parts of the body.
With the help of numerous anatomical analyses, Carla Stecco has produced an atlas of fasciae. Her findings are groundbreaking. It's the first time in the 400-year history of medical anatomy that the fascia of the entire human body has been systematically documented.
At first, I didn't understand anything. When I performed my first dissections, it all seemed to be chaotic. I couldn't see a clear picture. But then, very slowly, I understood how I could identify the fascia. Now it is fairly clear what the fascia is, and that is what I wanted to show with my atlas.
She's now examining the thoracolumbar fascia, which surrounds the muscles of the back.
In this region around the lower back, there's a particularly critical zone. There's a reason 80% of people suffer back pain.
The large back fascia. Researchers haven't yet been able to unlock all its secrets, but evidence points to its significance for many types of back problems.
We have now isolated the thoracolumbar fascia, the most important deep fascia in the human body. It is now being studied by so many researchers because it appears to be the cause of unspecified back pain.
The fascia of the back are among the most important fascia in the body. But how can fascia cause pain? Why do these layers of tissue in particular cause so much trouble? Robert Schleip is one of Germany's best-known researchers on fascia. Ever since he discovered how fascia is connected within the human body and how important movement is for our connective tissue, he's exercised every day with a skipping rope. Schleip is a trained psychologist and physiotherapist who, like many involved in fascia research, came to the field seeking answers to problems he saw daily in his practice. To discover what he was feeling with his hands, he took a sabbatical and devoted his energies to scientific study. He did his postdoctoral thesis on fascial tissue at Ulm University's Institute of Applied Physiology. His findings have won awards.
It's a bit like a fairy tale, because the fascia really was a kind of Cinderella. Something like the plump, spotty kid at school who gets laughed at, but then suddenly gains recognition. For me, it is a deeply moving story, and one that is also true. In the past, the fascia was seen as a disposable organ. Classical anatomists were happy when they had removed this colourless, sticky tissue to expose the actual muscles and organs. But in recent years, this structureless organ has attracted so much attention. And that, to me, is a really exciting development.
Robert Schleip wants to determine the diverse functions of the long underestimated fascia and find out what this fibrous white tissue actually consists of. The fascia is comprised of fibroblasts and a surrounding structure known as a matrix. Fibroblasts are the cells of the connected tissue. Among other things, they produce the collagen fibers that the matrix largely consists of. Effectively, the fasciae build up a home out of collagen.
Interestingly, the cells in the fascial connective tissue only account for very little of the tissue's volume, but they constitute a large part of the rest. I like to compare it to ants that have built a large anthill together, even though they themselves make up less than 10% of the volume.
Together with anesthesiologist Werner Klingler, Schleip is on a quest to understand fibroblasts, the jack-of-all-trades in connective tissue. Thanks to the collagen, the fibroblasts have a healing effect. If we cut ourselves, they close the wound. But too much collagen can also be harmful. Schleip and Klingler have studied how the tissue in an arm changes when it's put in a cast after an injury. Their study confirms that exercise is extremely important for the fascial tissue.
After 3 weeks in a cast with no movement, the tissue in the arm has begun to overgrow.
Picture A on the left shows healthy, undamaged tissue before the arm was put in plaster. Picture B was taken 3 weeks later. The change in the tissue is unmistakable. It has become matted, the structure thicker and chaotic.
The data we've obtained show quite clearly that a lack of exercise results in overproliferation of the connective tissue structures, and thus in a loss of function. This is the decisive discovery. It means that exercise is essential for maintaining our fascia.
Too little exercise and bad posture can cause fascia to become so rigid it can even compress nerves and muscles. Exercise, we are told, is a key to good health. Movement is also vital to maintain healthy fascia, which needs regular stimulation. Otherwise, it agglutinates or becomes stiff. People with desk jobs who do not do sports to compensate are likely to have fascial tissue that has become stuck together. What is more, office workers often suffer from back pain. So, is there a plausible link between agglutinated fascia and back pain? To find out, we traveled to Boston, which hosted the first major international conference on fascia 10 years ago. Helen Langevin from Harvard Medical School was among the participants. She specialized in fascia research early on. As a doctor, she was often at a loss to know how to treat patients with chronic back pain. She decided to delve further into the problem.
There's a lot of people who have back pain, chronic back pain, but when they have x-rays or MRIs of their spine, which is usually where people go to look for a cause of back pain, these studies are normal. Or there's no indication as to what would be causing the pain. And conversely, a lot of people have terrible looking MRIs, degenerated discs, but they don't have any pain. So we thought, well, what about the thoracolumbar fascia? Because it's a huge structure in the back. It really essentially connects the shoulders with the hips. It's a big sheet of connective tissue.
As we can see from an ultrasound picture of an arm, the fascia is arranged in layers. When we move, they slide back and forth. This also applies to the fascia in the back. In her research comparing the tissue of people who suffer from back pain with that of people who don't, Langevin has discovered that the difference lies in the connective tissue's ability to slide.
In normal people, we have two layers like this, and they should be able to move by about 75% of their length when the back moves. And then we know that in people with back pain, it's reduced to about 50% of their length. So we know that there's a reduction in the amount of sliding that occurs between layers.
Like her German colleague Robert Schleip, Langevin believes the cells of the connective tissue are responsible for this. Whenever they produce too much collagen, the sliding becomes more difficult. In experiments with rats, she's proved that exercise can counter this overproduction.
We do experiments where we induce a little injury in an experimental animal, very, very small injury, and then we randomize the animal to either stretching or no stretching. And the animal stretches twice a day, and this is a very kind of nice, very calm, gentle way of making the animal stretch. And then we find that the animals that stretch have decreased amounts of inflammation. They heal faster. Their injuries go away.
Wounds heal faster through movement and stretching. Under the microscope, Langevin discovered why. The fibroblasts expand by up to 200%. And not only that, the stretched cells also transmit chemical signals which cause the tissue to relax.
This was a new thing. What we found is, in fact, that the stiffness of the connective tissue is actively regulated from minute to minute by the fibroblasts. So this is a dynamic, active, cellular regulation of connective tissue tension. Now that could be important because what we're finding is that when you do acupuncture, for example, on the tissue, the fibroblasts actually respond and they expand, and that helps the tissue relax. The same thing with stretching.
Because active stretching and acupuncture have a relaxing effect on the cells and thus on the agglutinated tissue, we can actively do something about our pain. But what else, apart from too little exercise and incorrect posture, causes complaints? By studying the correlation between exercise, stretching, and back pain, Langevin has uncovered new approaches that offer hope of relief. Robert Schleip, meanwhile, is carrying out further research into the causes of back pain. For another experiment, he's securing fragments of fascia in an apparatus.
You could say that this is living fascia. Now we add different biochemical messenger substances, such as those that are active in tissue repair. Then we check the extent to which the fascia is able to contract on its own, independently of any muscles and nerves. We have some truly astonishing results.
The experiment shows quite clearly that the fascia contracts in response to the added messenger substances. It really does react independently of any muscular or nerve stimuli. And not only that.
What is really exciting is that we have also found messenger substances that affect fascia which are not only linked to inflammation, but also to emotional stress. It was a breakthrough for us to learn that the fascia also reacts to that very, very slowly and sustainably.
With this, Schleip has provided a possible explanation for something that has long been clear to many people with back problems, that emotional stress can cause physical tension and pain. The culprit is known as TGF, a signaling molecule. Its release is triggered by stress, a groundbreaking finding.
If I'm tensed up for weeks, even in my sleep, it is not mainly the red muscle fibers that are tense. They relax fairly quickly. It is the white fascia tissue, such as the sheath around the muscle. As manual therapists, we can feel that it is not the contents of the sausage, if we see the muscle as a sausage, but its skin, the surrounding membrane, that is hard. That's the mechanism we're now investigating.
In Maine, Thomas Myers offers training for physiotherapists, massage therapists, and yoga teachers from all over the world. His goal is to boost their awareness of the fascial network in their own body and share his years of experience.
I'm an autodidact, so I went and educated myself on this with the help of many of my students, my faculty, and a lot of good people along the way, including Louis Schultz and others. But really, I wanted to learn all that I could about fascia myself, and there's very little, well, back in the early 70s, there was very little written about it.
Myers is fascinated by the organization of connective tissue as a whole body network. The fascia ensures that we have a feeling for our body, that everything in it is in the right place and keeps us in shape. Fascia researchers call that tensegrity, a combination of the words tension and integrity.
Tensegrity engineering is an example of a different kind of engineering which comes closer to how you see the fascial system working as a whole system. So, as you can see, this is just sticks and rubber bands, and the piece is constructed in such a way that none of the sticks are touching each other. They're all held in place by the rubber bands. Now, if you take a skeleton, a standard classroom skeleton, the bones are wired together, and you make the presumption, oh, there's a skeletal frame inside me, and the individual muscles move that around like you know, the wires on a crane move a crane around. It's not true. Your bones are floating inside your connective tissue. If I could go boom and disappear all the soft tissue on your body, your bones would clatter to the floor.
This is a superb countermodel to our classic concept of the spine, to the model with the skeleton as a supporting structure, with the spine as a tent pole carrying the tent, which is softer. Until recently, that was how we imagined the spine. And here you see a nice tensegrity countermodel. These are the vertebrae, but they don't rest on each other and press down on each other. No, they are hanging. As long as the fascial elements, the rubber bands, have good elastic pretension. Then a vertebra may be worn down, but you can still stand straight, like a salsa queen in Cuba.
So the spine alone is not necessarily the cause of chronic back pain. Incorrect posture, lack of exercise, and stress are also contributing factors. If our tissue is to remain healthy, we have to keep exercising. But there's another crucial component: water. Our elastic connective tissue stores a huge amount of water, and that may be the greatest secret of the fascia. Depending on our age, the connective tissue can consist of up to 70% of water. The cells of the connective tissue, the fibroblasts, are important for binding water. In Padua, anatomy professor Carastecco has identified various functions of the fibroblasts.
Here we can recognize two cells. Both are fibroblasts, but they have totally different functions. This cell probably produces collagen. In the other cell, we see these tiny dots. If we magnify it, we see the interior of the cell, and above all, these tiny dots. They're proteoglycans, and in particular, hyaluronic acid. So we see how the two cells produce different extracellular substances.
Hyaluronic acid is a lubricant for our connective tissue. The substance forms further molecules of various sizes and degree of branching to develop a sponge-like network that can bind large quantities of water. The less hyaluronic acid our tissue binds, the less mobile we are. Carla Stecco's brother Antonio Stecco conducts research into hyaluronic acid at the New York University School of Medicine. From the example of an upper thigh muscle, it's clear that hyaluronic acid can be detected deep beneath the skin.
Here we see the dermis. And here we see the subcutaneous tissue, the fat, the superficial fascia, the deep fascia. And in the deep fascia there are, as you see, different layers of connective tissue. Between each layer we find hyaluronic acid. And in this region here we have more black space, which means there is more hyaluronic acid present.
Amid insufficient moisture, the tissue becomes rough and brittle like terry cloth. Hyaluronic acid provides a lubricant for the fascia to glide over neighboring muscle. In Germany, Robert Schleip and Werner Klingler are also carrying out research into hyaluronic acid. They're experimenting with therapies to improve the moisture content of the fascia and its sliding capacity. First, they measure the water content of the tissue.
We're hoping that manual stretching therapy will cause the water content to rise again. The great thing is, we believe that through this exchange of tissue water, inflammatory substances will be removed and the tissue will be cleansed.
The measurement points to a fairly high moisture content. Using a special massage technique, Robert Schleip now presses down firmly on the fascia in the subject's back.
These old Rolfing techniques that target the connective tissue are the most efficient we have found and tested so far. With this method, powerful pressure is exerted very slowly on the skin. You have to imagine it like slowly forcing the water out of a sponge in such a way that every pore is emptied. You don't do that whoosh whoosh, but really slowly.
The recorded measurements seem to confirm that through manual therapy, the water reserves in the fascia can be replenished and the suppleness of the tissue restored.
This was prior to treatment. Here you can see how we pressed out the water as if from a sponge. Then when we stopped with the mechanical treatment, the tissue filled up with water again. Here we had an interesting result. If we exerted enough pressure, the sponge was even more moist afterwards than before. In other words, you press the old water out of the sponge. And if you do that forcefully enough several times, the sponge is even more moist than before, which of course is interesting for us.
The idea is that massage realigns the collagen fibers and the fibroblasts produce fresh hyaluronic acid. New water replaces old water, enabling the fascia to slide more effectively again.
There's no doubt that massage stimulates the cell metabolism. But active movement brings even more dynamics into the tissue and results in a rise in body temperature. That already stimulates the metabolism. Each rise in temperature of 1 degree Celsius results in roughly 10% more enzyme activity.
It appears that with regular exercise, the fibroblasts can start to produce fresh collagen and free up matted fascia within just 3 days. But it can take up to a year for the agglutinated tissue to regenerate entirely. Exercise is important, but the right dose is crucial.
After exercise, we find microscopic injuries in the tissue that look like spiders' webs. So after exercising, one would be wise to consider resting for 1, 2 or 3 days to assess how much tensile stress should be applied to stimulate regenerative renovation work by the builder cells, the fibroblasts. These weave new, more youthful and durable collagen into my lumbar fascia or into my Achilles tendon. So the ideal setup would be alternating high doses of tensile stress with a 2 to 3 day break.
Und dann meistens 2-3 Tage Pause. Das wäre ideal.
Fascia appears to have an important and unsuspected impact on human health and well-being. International research on fascia has shown that relaxing and stretching connective tissue fibers helps alleviate back pain. But to what extent can traditional medicine help? Helen Langevin has studied the role fascia plays in acupuncture.
My interest in connective tissue and therefore eventually fascia began when I was studying acupuncture. When you manipulate an acupuncture needle, you have to insert the needle and then rotate it back and forth slightly. And what happens then is that you feel something. The acupuncturist actually feels that the tissues are tightening around the needle. That's what got me interested in, well, is this important in the mechanism of acupuncture? Because that had not been researched before.
Is it just the acupuncturist's subjective feeling that something is tugging at the needle when it's inserted and extracted? Or is there really a reaction in the connective tissue? Langevin wanted to find out.
We first wondered, well, is that measurable? Can you measure it? You can feel it. Can you measure it? So we did experiments where we used like a robot that inserted the needle and then rotated the needle back and forth and then pulled the needle out to measure the force that it would take to pull the needle out. We figured, well, if the tissues are really grabbing the needle, the force should increase after you manipulate it. And we were able to demonstrate that.
Every time the needle is inserted and removed, collagen coils around it like spaghetti around a fork. The sensation of a tug on the needle that therapists have long observed now has a scientific explanation. What's more, fibroblasts respond to the needle, even if they're several centimeters away. This effect is also visible in an ultrasound. But what exactly does the acupuncture needle trigger in the fascia? And could this mechanism of fibroblast activation within the fascia also explain the pain-reducing effect of acupuncture treatment?
The fibroblasts that are inside the tissues, up to several centimeters away, not just only at the needle, they expand. They respond, it relaxes the tissue. There's another thing that happens, which we are interested in, is that it releases a substance called ATP. So ATP is a signaling molecule. And so the ATP is something that we think may be possibly related to the analgesic effect of acupuncture.
And so modern research is providing evidence that validates ancient healing techniques. Until recently, the intervertebral discs were viewed as the primary and most frequent source of back pain. But now there is an increasing focus on fasciae as the trigger for chronic complaints. Analgesic researchers are also interested in the potential that fascial tissue offers for new therapeutic applications. German researcher Siegfried Menzer from the medical faculty Mannheim was one of the first to recognize the medical importance of fascia. He began exploring the extent to which fascia itself is pain sensitive. For that to be the case, it would need to contain encapsulated nerve endings.
We've conducted experiments in which we tried to determine whether there are any nerve fibers and individual nerve endings in the large fascia of the back. And what we have here is a relatively dense network of nerve fibers.
These point-shaped structures are nerve endings in which Menzer detected the substance P. P stands for pain. The small visible dots are pain receptors. But how can we know if the pain originates in the fascia rather than in the muscle? After all, fascia and muscles are virtually inseparable. Menzer uses a pair of delicate watchmaker's tweezers to irritate the fascia and measures the subject's pain sensitivity. Then the muscle is irritated, and sensitivity is measured again. The results are compared. Is it the fascia or the muscle?
Every vertical line is an electric signal. Using tweezers on an anesthetized rat in the same way that I just demonstrated, we squeezed the fascia. And here, you see that the frequency of these electric signals increases. So what one can definitely say here is that the effect of an irritation of the fascia on this nerve cell is much more pronounced than the effect on the receptors in the muscle.
Fasciae are permeated with countless pain receptors, making connective tissue our key organ of sensory perception. This has been proven without a doubt. Like Robert Schleip, Siegfried Menzer and his team also believe that stress has a direct impact on fascial tissue. And that brings the sympathetic nervous system into play. The sympathetic nervous system is part of the autonomic nervous system. From the brain through the spinal cord, it leads to almost every organ. We cannot control it. In stressful situations, it triggers what's known as the fight or flight response because it evolved as a survival mechanism. It causes a quickened pulse, sweaty hands, and a quivering voice. But how can it influence fascial tissue? Menzer gathered data to answer that question.
This here is a typical image which has confirmed our assumption that these fibers are indeed present in the fascia. You see here a mesh of nerve fibers. And if you were to enlarge it some more, you would see again the small point-like enlargements of these fibers, which are most probably sympathetic fibers, which means when these fibers are irritated, for instance through stress, then they release substances that cause the blood vessels to contract. And that could be one of the mechanisms that could explain why patients say their back pain worsens under stress.
International research on fascia has made huge strides in recent years. It's offered hope for progress in many scientific fields, including cancer research.
If we find that stretching can improve fibrosis and inflammation, it's natural to wonder whether it might reduce the growth of cancer and secondarily to that. And that's an area that we're looking at.
I'd never have expected the field of oncology to suddenly be at the forefront of areas interested in fascia research, and it's yielded an important contribution. So I wouldn't like to predict what the future will look like. I think this is a field that still has many surprises up its sleeve.
The findings of fascia research have shown that this body-spanning network of connective tissue, disregarded for so long, may be the place where inexplicable disorders and pain originate. And because of that, the place where healing can begin.